Do you remember what we learned last lecture? I think we're now pretty on track, so stabilized. So I'm not going to, I think I don't need to repeat the homework deadline 2 weeks before, right? And then the Wednesday is quiz day. Practice set is going to be posted today. But let's talk about the final project a little bit, because I saw a couple of concerns of what you have to do for the final project. We still have a time, by the way. Team should be consist of the 3 people, so then we're gonna have a 7 team. And the scope, actually, this is the amount of task I expect is about the final exam level test. What it means that I don't know how long you takes, how much time you spend to prepare the final exam. Probably 2 fully dedicated days. Anyway, that's the amount of the work I expect. I want to see in the final project presentation and report. What it means that definitely it's okay go beyond that, but no need to worry about your effort is not excessively large. As long as it goes across that bar, then it's a fine. Topics can be any robotics problem, including the multi-degree algorithm system, kinematics, dynamics, or control. Uh, Topic is very broadly defined. For instance, last year, one team actually doing the state estimation project, how to help the perception-based state estimation using the kinematics, something like that. That's also question.
Like your computer vision, or you have to use some dynamics,
Mm,
like SLAM.
Doesn't need to include the dynamics, but somehow including the kinematics is required. But by the way, SLAM is already using orientation matrix and transformation matrix. So it also includes some part of the topic. What I want to say is that don't need to constrain the every details in the topics we covered in the lecture. As long as it's robotics, then it's pretty open. So you're also welcome to bring any project you already have. But more important thing is this one. Topic should be properly selected. This, you don't need to worry too much about it. We're gonna continuously discuss. And then there is the period you have to actually send me the team member name and the title. So it's going to be all cleared at the moment you present your final project. But this is important, the literature survey and problem definition. So this, I hope that you go through the at least, the preliminary version of the paper writing, entire paper writing process. And one of the most difficult and time-consuming part is a literature survey. So make sure that you read at least the 3, 4 paper related to your topic. And then define the problem clearly. Clearly means that you see this related work and you found that this is missing hole, or you found that this is specifically interesting, so I'm going to tackle that problem. So that kind of statement should be clearly defined. It's okay, you don't have novelty, but if you want to duplicate the task, duplicate the algorithm written in the certain paper, then you have to clearly mention that this is duplicated work. I want to copy what they presented. That also nice final project. But here, sufficient challenges should be tackled. So if you replicate the other one's work, you download their code and run and it work, then there is no challenge, right? At least except the coding part, there is no significant challenge to be the final project topic. So you need to describe what kind of difficulty you went through and how you tackled. And that probably, these two, probably the most important part of the final project. And then writing. So this is our entire semester timeline. We are here. By the way, hopefully, we want to say goodbye to kinematics today and then move on to the dynamics. We'll see. This is important day of the final project. You need to submit your team members' name and the topic. It's right after the first week of November. And you have a 1 month approximately until the final project presentation. And then after a week, you submit the report. That report is this 3-page IEEE conference style paper, including figure and reference. So writing is not going to be entire 3-page, 2-column paper. You're gonna put some figure, some reference, which is going to take about a quite good amount of the space. Title, author, abstract, intro, result. These are all just standard format of the paper. So you should have all these follow this standard formatting. And again, the intro need to have some prior work and related work. Again, also doesn't need to be novel. No need to worry too much about you need to come up with new algorithm or new idea. That's okay. It's can be a bit beyond the. Of course, it's nice to have, but doesn't need to be. But have to say that that's not a objective. So if you have something you want to tackle, even though even though you think that that's not significant, but need to be clearly mentioned. That's more important. Significant versus truth. Yeah, of course, truth is much better. Any question? If you don't have, let's move on. So this is the things we learn last lecture. SE3 use the SE3 to find the fold kinematics. And you remember how we do, right? We know that the local frame to another local frame. So we always thinking about the one joint by one joint. Once you build up the all SE3 transformation matrix, what you need to do at the end is just multiply all together. So final equation formula can be a bit tricky to interpret, but the first matrix, individual matrix, is pretty understandable, right? So that's how uh, we build up the formula and find the fold kinematics. Does that record everyone's mindset? You remember, you didn't forget, right? Because today lecture going to be a bit confusing if you're already forget about this. So homework 3 is about the kinematics. This is a 60-degree of freedom system. As of course, you're gonna writing the code. You're gonna need help from the computational tool. So you are going to use the Python code. But keep in mind, this is not exactly same as your small, cute miniature arm. Configuration is different. Uh, Specifically, this one started from the roll, yaw and pitch, and the next one is roll, right? But this one, the homework problem is just sequentially another pitch and then roll. So don't be confused by different joint configuration. Anyway, the problem basically asking you the same question I asked in the homework 1, fold kinematics and inverse kinematics. But to solve this inverse kinematics, we have to actually calculate the Jacobian. You remember that, right? And today we're gonna learn how to build a Jacobian. It's going to be interesting. Let's recap the couple of things we learned already. So we know that Jacobian is the function of the joint position, right? It changed as the joint position changed. there is the function, couple of functions we learned. One is joint position to Cartesian position. What is the name of that function? Yeah, fluid kinematics. And the other side, the other way, Cartesian to the joint position is inverse kinematics. Okay, let's move on. And then joint velocity to Cartesian velocity and the effector velocity. Yes, Jacobian. And then Jacobian inverse. And this dagger means a pseudo inverse. Because in many cases, it is not square matrix. Sometimes, actually, many times, it is not invertible. So pseudo inverse. Okay. So we are going to talk about the velocity a lot. Let's check the previous example. But this time I'm asking something a bit different. What's the velocity, this velocity, omega VQ and omega Q in the quadrilateral frame? So we are going to put the six dimension vector to represent the velocity. They say spatial velocity, but no need to worry about. It's going to just omega and the velocity. If I write down this velocity in the quadrilateral frame, then omega q show up in the y-axis. So 0.5 here, right? And 0. And linear velocity is also pointing y-axis, right? So 0, 1, 0. Simple, right? Okay. Can you do the same things about the T-frame? So that this is actually better to write in this way. Quadrilateral velocity seen in quadrilateral frame. So once the quadrilateral velocity seen in tree frame, omega hertz. Anyone want to speak up? Can you see the frame? The frame is not aligned with X, Y, Z is a bit different, right? But you can see it. So now 0, 0, because it's aligned with the Z-axis, right? Positive Z-axis. And then this one probably same, right? 0, 0, 1. Am I right? Yes. Is it same or is it correct? Correct, right? Why everyone doesn't have a confidence? I mean, just read that VQ in this frame. Free frame is pointing G here, Y here, X here, right? Maybe it's because right. I mean, is this because vector? I can. So this is tree frame, right? And quadratic question. Okay. Yeah, this one. This means that I see this velocity, quadratic velocity. Maybe it's more clear if I write it in this way. So this one is a frame, and this one is a vector. I mean, I don't have a name for that vector, so I say just a Q. If next time I'm going to use this VC, something like that. But anyway, this represents what vector I want to describe, and this represents what frame I want to use to describe the certain vector. Okay, then now it's all clear, right? Let me draw the Q frame as well. Q frame, in case of Q frame, this is Y, this is X, this is G, right? So we can just read the same vector in this frame. So that's pretty simple. But we also know how to use the rotation matrix to do the same things, right? What is the rotation? The equation going to be if there is the R, P, Q, then what we can do to find this one is that R, P, Q times, let's say this as a spatial vector. Let's say this is a spatial vector. Frame P. By the way, I'm just using the V hat to represent omega and V. Is there any better? Let's say S. Spatial. S. 2, 1, 2. Then we can get this spatial velocity describing the frame T. What is the RTQ? Let's start from the first column. If we read the x-axis in T frame, and it's the same 1, 0, 0, right? And read the y-axis in the tree frame, give us 0, 0, 1, right? And what's the next last column? What? 0, -1, 0, right? And let's multiply the angular first. 0.5, 0, give us 0, 0, 0.5, right? If I multiply linear 0, 1, 0, then it's going to be 0, 0, 1. So yeah, equation work, right? Just rotating. See the same vector in a different frame with a rotation. So far, so good, right? We already did multiple times. We already did this multiple times. Okay, next question is if there is an arm attached to this quadrotor, so then this arm is going to move together with the quadrotor, right? Then the things we have to understand is not only this frame transformation, we actually need to also think about the momentum and the cross product thing. So are you familiar with this equation, P cross product omega? So if you have a momentum, rotate, then you see the linear velocity at this point, right? Angular velocity, if there is a rigid body, this big rigid body, okay, let's use this one. We already have this. And make this posture. And then let's rotate this first joint. And every joint and link of this arm having the same rotation, angular velocity, same angular velocity, but linear velocity are all different, it depending on the momentum length. So in case of the end effector, you're actually watching the linear velocity to the y direction, right? When you're rotating this way. And that equation, the equation we can use to get the linear velocity is this one, P cross product omega. So in this case, the P is 0.5, 0, 0.5, right? Let's check the only first. Without thinking about this size, let's think about the how much, what is the direction of the linear velocity? Because this one rotating in this way, you're gonna see this vector, right? And the length of this arm is basically the same. So same for the x direction, same for the y direction. What it means there is a 45-degree, right? And we're gonna rotate this arm in this way. And we're gonna see this vector, and this vector going to have 0 to y-axis, right? And then to the x is going to positive some number, right? And to the y, going to same but negative some number. Does that make sense? And this size is going to be determined by this momentum. And P cross product omega, what we can do, is there anyone who memorized the cross product multiplication? How should I do?
I think it's like putting ijk on top and then first vector, second vector, and do a determinant.
Okay, that work. Let me give you another way. Just putting this P in the skew symmetry matrix form, and then do just the normal matrix multiplication. That's gonna give you the also cross product. So this P cross omega is actually same P omega. So let's see it is actually working. Okay, our P is 0.5, 0, 0.5. So our cross product form of skew symmetry form of this P is, do you remember the equation? Minus x, y, minus g, or 0 in diagonal term, and just make the symmetry, but with a different sign. So 0, minus 0.5, 0, minus 0.5, 0.5, 0.5, and 0. So if I multiply this with the omega matrix, omega vector, which is 0, 0.50, and I should be able to get some vector similar to this one. Let's do that. Minus 0.25, 0. Okay, let's see. 0.25. What happened? XYG 0.5. This. Y-axis minus P cross product. Oh. Can you find any error in the formula? Omega Q is Y positive. Ah, okay. I made a mistake.
What would be P cross omega?
Yeah, you're right. This is not P cross omega, omega cross product P. Yeah, this. You're right. Omega cross product P. This is actually showing the good omega cross product P is same as minus P cross product omega. So this is one of the cross product calculations idea. Oh, sorry. Is that okay? I hope my mistake makes things more clear. Okay, so here this calculation, the linear times omega giving the actually displacement time the angular velocity giving the linear velocity give us the one important idea. We can use these things to calculate the Jacobian because joint going to rotating in their local frame, and I need linear velocity because of that angular velocity at the end effector. So if we just stacking up this velocity, then we can get the linear velocity of the end effector because of the entire joint velocity. So process is kind of like this. Let's say there is the first joint rotating, and this first joint rotation going to show up as the rotation, right? In the second link, second joint, and linear velocity. And we have rotation matrix describing the 2 to 1 and the linear vector pointing this frame 1 from the point frame 2. And doing this again and again up to the end give us the end effector velocity. So what it's gonna do is that calculating the linear and angular velocity because of the S1 here, and then the end effector velocity going to be this plus this, the linear and angular velocity caused by a second joint. Does that make sense? So it's like when you're rotating the arm like this, then you're gonna see the linear velocity of this point, right? And then when you're rotating this joint, then you're also going to see the linear and angular velocity of the end effector because of this. The angular and linear velocity of the end effector when these two joints moving together is just the summation of these two velocities. It's like if you are a linear case, it's like this. You have a car moving toward the 3 meters per second, and then you are in the car, but also moving forward the 3 meters per second. And what's your velocity? Definitely 6 meters per second, right? Just add up. This is nice property of the velocity. Linear, angular, just summing up. Okay, when we write down this equation in a nice form, then we need something like this, order-joint mapping. And this order-joint mapping actually can give us the really nice form of the Jacobian. And let me describe this term. This term is angular velocity and linear velocity written in the local frame. And there is a really nice property of nice things you can get if we writing all the velocity in the local frame. Okay, I say that Jacobian is a function of the joint position, but if you are in the first joint frame, which is rotating together with your rotation rotation, then when I ask it, yeah, what's your spatial velocity in joint 1, then you're going to say 0, 0, 1, 0, 0, 0. This is the spatial velocity in the frame 1. Because you never gonna see the linear velocity. And the only angular velocity you can see is revolute yaw. So it actually independent of your joint positions because you're moving together. Second joint, so in this case, second joint spatial velocity is what? In your miniature. 0, 1, 0, 0, 0, 0, right? This is the spatial velocity on the frame 2, but only about joint 2. So S, this omega 1 and V1 is actually really simple term. There is a V1 because sometimes you have a prismatic joint. If you have a prismatic joint, then you're going to see the sum 1 here. If it is aligned with Y and move to the left, then the joint has a velocity, then you're going to see this. So good news is that in your homework and this miniature arm, you are going to see the all 0 always in the second part of your spatial velocity. Question?
If I have a prismatic joint that is connected to a revolute joint in the y-axis, and then the revolute joint points up, then the velocity becomes the z velocity, or is it still the y?
So if you have a certain joint having that kind of weird behavior, then it becomes a bit complicated. The most important thing you have to see, actually the recommended thing is that if your rotation change the prismatic joint's direction, then put the another frame for the linear part. So then you don't need to worry about that part, right? So we're still talking about the end effector velocity. If I can just multiply theta 1 dot and theta 2 dot here and summing up give me the end effector velocity, then we are all happy, right? So that's why there is the other joint to make our life is unhappy. Of course, that's not the end of story. So this one is actually written in the local frame. So we need to write this equation, this frame, this spatial velocity in the end effector frame. And that's what other joint do. Other joint is defined in this way. Right. This one, omega, the angular part, going to be another angular part through the orientation matrix, which we just did, right? So this one going to be multiplied the orientation matrix. And this linear velocity term going to be also goes through this orientation. So we need to change the orientation of the linear velocity. But also cross product P need to be added. And this omega is actually this one, right? So that's the end of the story. So omega cross product P plus R linear velocity is the linear velocity we're going to see in the end effector. And if you write down this formula well, then you will answer with this formula. Question? Because when you have an angular velocity in the first frame, that angular velocity going to be linear velocity, some amount of the linear velocity at the end effector. So we need to account that effect. So other joint mapping is actually 6x6 matrix. Question?
Oh, yes. I was wondering why you can multiply it all.
Yeah. So spatial vector is a 6, and yeah, of course we answer with a 6-dimensional vector. So we need a 6x6 matrix, and this 6x6 matrix is written in R, Geo here, and P cross product R. This oh. Okay, let's try this. That's how this lecture working, right? I explained the formula check that that formula is true. Do this together. Let's do this together. So for your insights, align all the joints at the 0 position. Then and then imagine that this third, fourth, fifth, sixth joint are fixed. Then we are going to get the same 2 degree of freedom arm with this formula or with this diagram. Make sense? Okay. So the goal is finding the Jacobian. And the Jacobian equation is going to be this. Say ND factor first term is the joint T E to 1 S1, other joint T to 2 S2. Let's start from the nice part. S1 is 0, 0, 1, 0, 0. Because we are using the same local frame like this. And S2 is the 0, 0, 0, 1, 0, 0, 0, 0. Right? So equation going to be this. The question is how to get this odd joint. S1, S2, we already did. Let's do the second joint first, because it looks easier. Can you see what is the orientation from the EE to 2 and the factor to 2? Is it any joint position associated with this orientation change? So you actually can see that this frame versus second joint frame is constant because we define the second joint frame after the second joint movement. So it always actually pointing the end effector with the x-axis, and there is no joint position associated with it. So the T end effector to frame 2 is simply identity and minus 0.2, 0, 0, and 0, 1. Right? I agree. And all the joints of this is again identity, 0, T cross product, so identity and identity. So I'm going to just ignore this part. T is T is 0.2, 0, 0, 0, 0, 0, minus 0.2, 0, 0. Right? And this one, 0, 0, 0, 1, 0, 1, 0. So multiplication of this 6 by 6 times 6-dimensional vector give us same first part. And this part, I mean, this identity is going to multiply 0 vector, but this one is something, needs some, I don't know, care. 0.010 going to multiply sequentially. First, 2 going to be same, but minus 0.2 going to align. Are you with me? But we can check this result. Okay, let's see this result is correct. Because there is always, you already seen it, high chance I made a mistake. So the question is something like this. Anyway, this is the other joint EETS2, this term, right? So second column of the Jacobian. When we calculate the Jacobian, then we are going to multiply this with the theta 1 dot and theta 2 dot. Let's say theta 1 dot is 0, then only theta 2 dot going to make an end-effector velocity change, right? So let's move this to positive direction, second joint. So then, end-effector must see y-directional angular velocity change, right? How about linear part? Plus x or plus y or minus x minus g. What is this movement means? So you have a nice small and cute arrow system, right? Frame system. And you see this end effector moving. By the way, you all know that this is positive, right? Downward, right? What it means that you see g direction of velocity, but in a negative direction. And the size of this linear velocity going to be scaled with the momentum length. So that's why you see the minus 0.2 here in the very last term. Question. Because our y is aligned in this way, right? So this rotation is positive. So we are going to rotate in this way. When the theta 2 that is, for instance, 1 radian per second. So then this end effector move downward. Does that make sense? So minus 0.2. Happy? Okay, let's move on. We need to do the other joint one. Right? Everyone fine with it? The one is a bit more than just identity 0.2. So let's put this together. Okay, R EE1 P EE sin in 1 and close photo R EE1 R EE1 and 0. So what's the R end effector to 1? And here is a important question. This one should change this number, this R, the orientation of the first frame with respect to the end effector frame should change as this robot changes the posture, right? Because it's going to be seen differently. It is function of first joint position? Yes or no? Is that end effector frame, is the first joint frame with respect to the end effector change because of the first joint movement? Yes or no? No, right? So first joint frame 1 is the only function of the theta 2 because joint 1 frame is also rotating together with the joint 1. So we're not going to see any change if the theta 2 is fixed. So then you can see that what is this rotation matrix? This rotation matrix is nothing but R Y theta 2 transpose. Why skip too much? Okay. So from the first joint to the end effector joint, we know it is only the function of the theta 2 and the theta 2 rotating around the y-axis, right? But it means that when you see the frame end effector from the 1, then you're gonna see cosine theta 2, 0, 1, 0, 0, 0, sine theta 2, minus sine theta 2, cosine theta 2. Right? So a simple way to check this is that putting the theta to 0, then you're gonna see identity. Putting the theta to 90 degree, then you should see that x is actually pointing upward, right? So theta 90 degree give us the x-axis become a 0, 0, 1. Okay, sorry. This is minus 90. If I wanted to rotate it 90 degree in this way, I cannot do. So minus 90 degree give us this one becomes 0, this one become a 1, right? So x-axis is actually pointing upward, which is also makes sense. So this is the transformation, actually rotation change, rotation frame end effector frame orientation with respect to the first joint frame. Does that make sense? Please say yes. This is the orientation only governed by the second joint, right? And then if I want to see the same things the reverse way and the effector to the 1, then we just take the inverse of this orientation matrix. That's why the REE1 is RY theta 2 transpose. So let me down this. REE1 is nothing but putting sign minus here and plus here. Great, right? So now the last thing is this one. The vector pointing the first joint. Okay. In the 0 position is minus 0.2 to the x direction and minus 0.15 to the g direction, right? In this posture, right? In this posture, in EE from EE to go to the frame 1 from the EE, then you need to go backward 0.2 and downward 0.15. So that's why we can do this. The problem is this one, this 0.15 part, is changing depending on the joint position, second joint, right? So for instance, if second joint is minus 90, then this going to be x direction of minus 0.2 and another x direction minus 0.15. And if that makes sense, it is not g direction minus 0.2 because your local frame and the effector is rotating together. So this direction of movement is still x. Okay. So the P and the effector to 1 is minus 0.200 plus R EE to 1 0 minus 0.15. Okay, if this is a bit confusing, I mean, it's not intuitive, then we can do it in this way. So let's say we are rotating a frame theta 2 degree, and there is the vector pointing downward, and we're gonna lead this vector in this frame. So then this is x, this is g, and it looks like, I mean, y is pretty simple, 0, right? And the x is minus 0.5, actually 1015 pi. This is theta 2. Sine theta 2 minus 0.15 cosine theta 2. Right? Plus minus 0.2 give us the P and effector to 1. Are you fine with it? Do you want to check this one is actually true? I kind of. Okay, I think that's true. So this one is this one. So C2 0 minus S2 0 1 0 S2 0 C2 times 0 0 minus 0 1 5 give us this time this 0 1 5 S2 and all 0 minus 0 1 5 C2. Whew. Okay, so far so good. We didn't make any mistake. I didn't make any mistakes. Okay, P. We have a P. Minus 0.2 plus 0.15 S2 0 minus 0.5 into. Oh, we need to make auto joint mapping. C2 0 minus S2 0 0 S2 2 0 C2 0 minus S2 0 S2 0 C2. Oh, now is this one. This means that there is the also C2 blah here, and we need to make another 3x3 cross product skew symmetry matrix, but some whiteboard management issue. 0.2. Can you do in your paper sheet as well? Because it's going to be very small. 1.5 S2 0 0.15 C2 0 0 0.2 minus 0.15 C2. And S1 0 0 1 0 0 0. So now you can see that why S1 is so simple, right? Because all the complexity actually condensed here. Rotation part is relatively simple, right? Multiplying this with this give us minus S2 0 C2. Let's first check this is true. Okay, this means that when the theta is 0, so when the theta means that theta 2 is 0, then we're going to see 0, 0, 1. So basically same rotation in the end effector, right? And if it is 45 degree, so pointing in this way, this rotation going to show in the X and Z together. Does that make sense? Because the X-axis is also pointing a little upward. G-axis is also pointing a little upward. So this rotation going to be shared by X and Z. Okay. I see that you cannot accept, but don't know exactly how I ask. So one easy way to think about is this rotation is how the rotation is shared with the other axis is that just keep thinking about this hand vector, which is rotation axis vector, as a linear velocity. So in this case, this rotation vector is this one, right? And when you move this vector in n-effector frame, you see that x and y is actually influenced by this one. This vector has the x component and g component, right? What it means then, in the local frame, you're gonna see the some roll movement and yaw movement together to make this rotation. So it's like this.
I have like a third going or something to get increasingly more complex, or is it just dependent on like the last? So like,
It's going to be more. It's all. I mean, the question is, for instance, if you have a this, and now you can see that this 45 degree actually making this axis is represented by all three axes, right? So yeah, it becomes more and more complicated. But the good thing is that the last one, the very close to the at the end, which is closer to the end effector frame, is relatively simple. It's going to be always a bit simpler. And probably this is good question. So when you're rotating the theta 2 here, and I say that there is the omega 1, the first joint axis in the g direction, then it's shared by x here, y here, right? And if we just interpret this process in the linear velocity wise, then you're gonna see the cosine theta of this term is represented as omega 1, omega x, and sine theta times this one going to be shown as the g-axis rotation, right? So then it seems like this is plus, right? Once in rotating in this way, then you're gonna see that some positive rotation to the roll direction, some positive directional rotation to the y g direction, yaw direction, right? Then why we have a minus here?
it's going to take it in
No. Sorry. The answer is very simple because I rotating this to the minus pi over 4 degree. So this is not, 45 degree rotation. This is actually minus 45 degree rotation. So the number I need to put here is minus pi over 4. So then you can see this is plus, it's also plus, right? So that's why it's positive. Okay, I didn't like anything. The last one, yeah, I did this one time, but it's not actually really helpful to intuitively understand. So this part, linear part, I mean, this one is, we can just ignore it because this one going to multiply together with this zero vector. But this one, it's once you multiply this one with this omega right before this cross product, it's actually same as this one. So to calculate this component, what we can do is just multiply this with the cross product skew symmetry matrix of this one. Makes sense? Because this is also R. So what we need to do is the P skew R times omega. So we can just use this as a middle vector. So then equation going to be, let's remove this one. Zero, 0.2 minus 0.15 is 2, 0.15 C2 minus 0.15 C2, 0 minus 0.2 plus 0.5 S2 times minus S2 0 C2. Then O0 in the first X and plus 0.15 C2S2 plus 0.2 C2 minus 0.15 S2 C2 and 0. Yeah, I see. I can see it's not ends up with, very intuitive number. But one couple of things we can see is X and Z is 0. What it means that whatever joint position on the second joint, we cannot make an X directional or G directional linear velocity with the first joint, which makes sense, right? You cannot. When you actually do this, and you're gonna see that what you can do is the only Y directional velocity making. And this linear velocity also going to be just 0.2 times first joint velocity when the theta 2 is 0, right? So if theta 2 is 0, then you are going to rotating the entire arm like this. It's just purely governed by this length. So even though you have this long arm and has this short arm, anyway, you only care about this amount of the length, right? To calculate the Y direction velocity. That's why if you plug in the theta equals 0, then this term going to be 0 because of S2. This term becomes 0 because S2. This one going to be just 0.2. Question. But to make an X directional velocity, by rotating this one need to move forward, right? At least moving this way. I mean, actually this way, because local frame is pointing this way. You cannot make this directional movement or this directional movement.
Not like a diagonal vector, and then you can have like factorize it into X and Y directions. So it means that it's a tangent of a circle. Move in any direction.
So for instance, here, to make this directional velocity, then you actually need to rotating this arm this way. That's the only way, right? Even though you're rotating this way or any other direction, you cannot make this directional velocity, right? So the first joint term, first column, must not make a Y G directional component, right?
Right.
Actually, it's the same to the X direction. To rotating this cannot make this end effector moving this way.
In the
In the local, end effector plane, yes. Yeah, you cannot make this end effector is longer by rotating this. So next slide is actually in class exercise. So can you do the third column? Can you find the third column of this Jacobian? If I have another joint, so basically now you have this joint as well. We only have 5 minutes, so let's try it. I'm going to visit individually and see that what's going on.
That last joint.
What about the?
Oh, that's just the.
It's only it's breaking. It's rotating around the X, so it's still one.
Very.
1 0 0. Yeah, it's still right. 1 0 0 0 0.
And so.
For S three. Yeah, I think so.
Oh.
Yeah, so it's 1 5 0.
Yeah.
Okay, cool. All right, so now it's. I don't know what. So now we need to find E3, right?
Next would be the video or something.
This actually. So it's even though R3, right? Right, R3. Yeah, R3.
When you actually solve all the equation, then
What's
B?
I don't know if that, wait, it's, I don't fully understand this, right? At the bottom left. I'm just gonna get R3 first. That's easy. So that would just be regular, yes, 1 0 0 0 post theta, what is it, theta 1 or post theta 3 minus sine theta 3. Zeros, I think. Oh, yeah.
Yeah.
Okay. I was confused with the bottom left in the T matrix, like the. I'm just again a little unfair how you got the delta, like the. Oh, R. Okay.
So a Fourier equation is a sign the skip is or proper way of service is that you following
same plane, right? So then,
We're only voting twice. Yes. Yeah.
We did.
Okay, we can do this again one more time in the next lecture, but before you come, think about why this answer is this one. I give you just the answer. Answer is 1 0 0 0 0 0. So, please do the calculation yourself before the next lecture, before Wednesday. And this is the answer. This is the third column of this Jacobian. And we're gonna solve this together next in the next time. Thank you.
Make sure I have this.
Yeah, you have to. But here, when you multiply this one plus this and the first with this one, then you see that all these things multiply with 0.
So it becomes
So,
0 0.
yeah, 1 0 0. The linear part, let's see first. To calculate it, you have to make a P first, the cross symmetric matrix form multiply with this one, right?
So the P vector should be 0.100, right? It should be
So minus 0.1.
just going in negative.
Yeah, because the end effector 2 break.
Okay, so and the vector should be and that's gonna be negative 1.
Yeah.
And then this should be, I think, this product is with.
And then multiply.
Do I answer?
Oh, yes. Mhm.